Welcome to the lesson on the types of electrical circuits. In this lesson, we will explore the concepts of electrical circuits, focusing on three main types: series circuits, parallel circuits, and series parallel circuits. By the end of this lesson, you will be able to differentiate between series, parallel, and series parallel circuits in terms of their configurations and characteristics. You will learn how to calculate the total resistance and total voltage of different circuit combinations. You will also be able to identify and differentiate between the three types of circuit configurations. The three main types of electrical circuit configurations are series circuit, parallel circuit, and series parallel circuits. Let us start with the series circuit. A series circuit is characterized by components connected end to end, creating a single path for current flow. This configuration has distinct electrical properties. The current remains constant throughout the circuit, flowing equally through each component. The total current can be calculated by dividing the total voltage by the total resistance. The total voltage in a series circuit is equal to the sum of the individual voltage drops. Similarly, the total resistance of a series circuit is the sum of all individual component resistances. Alternatively, using Ohm's law, the total resistance can be calculated as total resistance, R equals total voltage V divided by total current I. An important consideration in series circuits is that the failure of any single component disrupts the entire circuit as it breaks the sole current path. This arrangement is commonly used in applications where equal current flow is desired across all components, but it comes with the trade-off of increased vulnerability to single-point failures. Let us take a look at the series circuit rules. One fundamental principle of series circuits is that the total resistance is equal to the sum of all individual resistances in the circuit. To illustrate this, consider an example with four resistors. R1 is 2 ohms, R2 is 6 ohms, R3 is 4 ohms, and R4 is 12 ohms. To find the total resistance in the series circuit, we simply add these individual resistances together. Thus, R total equals R1 plus R2 plus R3 plus R4, which in this case equals 24 ohms. Another key rule of series circuits is that all electronic components in the circuit share the same current. This means that the current flowing through each component is identical, regardless of the component's individual resistance. To demonstrate this principle, let's consider the same example of the previous slide, where we need to find the total amperage of a circuit. Given a total voltage of 12 volts and a total resistance of 24 ohms, which we calculated before, we can determine the total current using Ohm's law. The formula is I total equals total voltage divided by total resistance. Plugging in our values, we get 12 volts divided by 24 ohms, which equals 0.5 amperes. This current flows through every component in the series circuit, illustrating the uniform current distribution characteristic of series connections. The third fundamental rules of series circuits states that the total voltage across the circuit is equal to the sum of the individual voltage drops across each component. Let's illustrate this using our previous example. With a current of 0.5 amperes flowing through each resistor, we can calculate the voltage drop across each one using Ohm's law. For R1, the voltage drop is 0.5 ampere times 2 ohms equals 1 volt. Similarly, for R2, it is 0.5 ampere times 6 ohms equals 3 volts. For R3, it is 2 volts. And for R4, it is calculated to be 6 volts. When we sum these individual voltage drops, we get 12 volts, which matches our initial total voltage. This demonstrates that in a series circuit, the voltage is divided among the components, with the sum of these divisions equaling the total voltage supplied to the circuit. Series circuits find application in scenarios where simplicity and sequential controls are required. Their straightforward nature makes them suitable for basic applications where components need to be activated in a specific sequence, or where a single path for current flow suffices. However, in modern complex electrical systems, series circuits are less common due to their limitations. These limitations include the susceptibility to failure if one component malfunctions, as well as the inability to independently control individual components without affecting the entire circuit. Typical examples of devices with series circuit includes flashlights, some decorative lightings, and battery packs of laptops, cameras, and power tools. A parallel circuit is characterized by components connected across common points, creating multiple paths for current flow. In this configuration, the voltage remains constant across all components, while the total current is distributed among the individual branches, summing up to the total circuit current. The total resistance in a parallel circuit is calculated uniquely. The reciprocal of the total resistance equals the sum of the reciprocals of individual resistances. This results in a total resistance that is always lower than any single component's resistance. A key advantage of parallel circuits is their resilience. If one component fails, the others can continue to function. This property, combined with its ability to maintain consistent voltage across components, makes parallel circuits common in basic electrical wiring and many practical applications where consistent voltage supply and circuit reliability are critical. Let us examine some of the key rules of parallel circuits. In a parallel configuration, the total resistance is always less than any of the individual resistances in the circuit. This is because parallel connections provide additional paths for current flow, effectively reducing the overall resistance. To calculate the total resistance, we use the reciprocal method. Consider this example with 4 resistors, 2 ohms, 6 ohms, 4 ohms, and 12 ohms. We first take the reciprocal of each. Adding these reciprocals gives us 1 ohms. To find the total resistance, we take the reciprocal of this sum, which equals 1 ohm. This demonstrates how parallel connections result in a lower total resistance, in this case 1 ohm, which is indeed less than any of the individual resistances in the circuit. Another important rule of parallel circuits is that the total current in the circuit is equal to the sum of the individual branch currents. This principle can be demonstrated through an example. Let's consider a parallel circuit with a voltage source of 12 volts and a total resistance of 1 ohm. As calculated in the previous example. Using Ohm's law, we can calculate the total current. I equals V divided by R, which gives us 12 volt divided by 1, ohm equals 12 amperes. Now, let us examine the individual branches. For the first branch with 2 ohms resistance, the current in 1 is 6 amperes. Similarly, for R2 with 6 ohms resistance, the current is 2 amperes. For R3, the current is 3 amperes. And for R4, the current is 1 amperes. When we sum these individual branch currents, we get a total of 12A, which matches our initially calculated total current. This illustrates how the current divides among parallel branches while the sum remains equal to the total circuit current. The third fundamental rule of parallel circuits states that all electronic components connected in parallel share the same voltage drop. This principle can be verified using our previous example. In a parallel circuit, the voltage across each component is equal to the total voltage supplied to the circuit. We can demonstrate this using Ohm's law. Voltage equals the current times the resistance for each branch. For the first branch, V1 equals 6 amperes times 2 ohms, which equals 12 volts. Similarly, for the second branch, 2 amperes times 6 ohms equals 12 volts. For the third, 12 volts, and for the fourth, 12 volts. As we can see, despite the different current flows and resistances in each branch, the voltage drop across each component is consistently 12 volts. Parallel circuits offer greater efficiency compared to series circuits and are particularly advantageous in scenarios where power needs to be distributed to multiple devices. By providing multiple paths for current flow, parallel circuits ensure that each device receives the necessary power without affecting others, resulting in efficient operation and optimal performance of the entire system. Additionally, the parallel configuration allows for customization of parameters such as resistance, capacitance, or inductance for individual components, facilitating tailored design and functionality. Typical examples of parallel circuits include household wiring, solar panel wiring, computer power supply units, etc. Series parallel circuits combine elements of both series and parallel configurations within a single circuit, offering a versatile approach to circuit design. These hybrid circuits leverage the characteristics of both configurations. Voltage adds up in series sections while remaining constant across parallel branches. Current stays constant through series components but divides among parallel paths, and resistance sums in series portions while combining reciprocally in parallel segments. This flexible arrangement allows for complex circuit designs where different components can receive tailored voltages and currents as required by the application. The ability to mix series and parallel connections within one circuit provides engineers with greater control over power distribution and component behavior, making series parallel circuits invaluable in a wide range of electronic and electrical systems where diverse operational requirements need to be met simultaneously. Let us examine some of the key rules of series parallel circuits. Here, calculating the total resistance involves a combination of techniques used for both series and parallel circuits. Let's consider an example to illustrate this. Suppose we have a circuit where R3 and R4 are connected in parallel, each with a resistance of 12 ohms. To find their combined resistance, we first calculate their reciprocals, which is 0.0833 for each. Adding these reciprocals gives us 0.166 ohms. Taking the reciprocal of this sum yields 6 ohms, which is the equivalent resistance of the parallel portion. Now, let's say R1 with 2 ohms and R2 with 4 ohms are connected in series with this parallel combination. To find the total resistance, we simply add these series resistances to our parallel resistance, 6 plus 2 plus 4 yielding 12 ohms. Thus, the total resistance of this series parallel circuit is 12 ohms. This method demonstrates how we first resolve parallel sections into their equivalent resistances, then add these to any series resistances to determine the overall resistance of a series parallel circuit. In a series parallel circuit, determining the total amperage requires first calculating the total resistance and then applying Ohm's law. In our example, with a total resistance of 12 ohms and a voltage of 12 volts, the total current is 12 volts divided by 12 ohms, which equals 1 ampere. To find the current in the parallel branches, we must first account for the voltage drops across the series components. The voltage drop across R1 with 2 ohms is 1 ampere times 2 ohms, which equals 2 volts, and across R2 is 1 ampere times 4 ohms, equaling 4 volts. These series voltage drops total 6 volts, leaving 6 volts for the parallel branch. Now, we can calculate the current in each parallel branch. For both R3 and R4, which are 12 ohms each, the current is I equals V divided by R, or 6 volts divided by 12 ohms, which equals to 0.5 amperes. This process illustrates how current behaves differently in the series and parallel portions of a series parallel circuit, with the total current flowing through series components and then dividing among parallel branches. Continuing our analysis of the series parallel circuit, we now focus on the third rule. The total voltage drop across the circuit equals the sum of all individual voltage drops. Using the currents we calculated earlier, we can determine the voltage drop across each component. For R1 with 1 ampere flowing through 2 ohms, the voltage drop is 1 ampere times 2 ohms equals 2 volts. Similarly, for R2, it is 4 volts. In the parallel branch, R3 and R4 each have 0.5 ampere flowing through 12 ohms, resulting in a voltage drop of 0.5 times 12 equals 6 volts for each. When we sum these voltage drops, we get 12V, which matches our initial total voltage. This calculation confirms that the voltage drops across the series components R1 and R2 add up to 6 volts, while the parallel components R3 and R4 each have 6 volts across them, collectively accounting for the entire 12 volts of the circuit. This demonstrates how voltage behaves in different parts of a series parallel circuit, dividing across series components but remaining constant across parallel branches. Speaking about applications, series parallel circuits are commonly employed in sophisticated electronic systems and industrial applications where intricate circuit designs are necessary to achieve desired outcomes and meet specific operational criteria. Typical examples where series parallel circuits are utilized are in industrial machinery, automotive and aircraft wiring systems, emergency lighting systems, etc. This table provides a concise comparison of 3 fundamental circuit configurations. In a series circuit, voltage is divided among the components, while current remains constant throughout, leading to a higher overall resistance. Conversely, in a parallel circuit, voltage is consistent across all components, but current divides among the branches, resulting in a lower total resistance than the smallest individual resistance. Series parallel circuits combine these patterns, exhibiting varying voltage and current depending on the branch. In terms of impact, a failure in a series circuit breaks the entire circuit, while parallel circuits remain unaffected by a single component failure, and series parallel circuits experience localized effects depending on the branch. These configurations find applications in simple devices, household wiring, and complex electronics, respectively, based on their unique characteristics and behaviors. Let us turn our attention to the type of electrical circuits in battery electric vehicles. BEVs typically utilize a combination of series, parallel, and series parallel circuits to manage the flow of electricity between the battery, motor, and other components. Here are some of the examples. In a high-voltage battery pack, the cells are most commonly connected in series to achieve the desired voltage. The motor is connected in series with the battery pack to operate efficiently at the higher voltages provided by the series connection. Auxiliary systems in BEVs employ various electrical configurations to optimize functionality and reliability. The 12-volt power outlets for accessories, such as phone chargers or small appliances, are typically wired in parallel, allowing multiple devices to be powered independently. Lighting systems, including headlights and taillights, often utilize series parallel arrangements. This configuration helps balance voltage requirements across multiple light units while providing redundancy, ensuring that if one light fails, others remain operational. The regenerative braking system in BEVs showcases a more complex arrangement, incorporating both series and parallel configurations. This hybrid setup allows for efficient energy recovery during braking, directing power back to the battery, while also providing the flexibility to engage traditional friction brakes when needed or to dissipate excess energy if the battery cannot accept more charge. Let us now summarize what we have learned in this lesson. Electrical circuits can be categorized into three main types: series, parallel, and series parallel. In a series circuit, components are connected end-to-end, forming a single path for current. The same current flows through all components, and the total resistance is the sum of individual resistances. Parallel circuits have components connected across common points, forming multiple paths for current. The voltage is the same across each component, and the total resistance decreases as more paths are added. Series parallel circuits combine both series and parallel configurations, allowing for complex circuit designs and different components to receive different voltages and currents as required. Battery electric vehicles typically utilize a combination of series, parallel, and series parallel circuits to manage the flow of electricity efficiently. Thank you.